distinguishing architecture design and implementation in software engineering. Before we dive into the challenges, let's define what we mean by architecture design and implementation. Architecture refers to the high-level structure of a system, including its components, connectors, and constraints. It defines the system's overall organization and structure. Design involves the detailed planning and structuring of components to meet both functional and non-functional requirements. It focuses on how different parts of the system interact and operate within the defined architecture. Implementation is the actual coding and execution of the system based on the architectural and design specifications. It translates design into working software. The key distinction among these is that architecture sets guiding principles, design refines specific details, and implementation realizes the system. Software specifications are typically divided into three levels: architecture, design, and implementation. However, in practice, these distinctions are often blurred. This leads to miscommunication among teams, confusion during the development process, and unnecessary debates about what belongs at each level. Our goal is to explore why this happens and how we can address it. Our discussion is based on the research paper, Architecture, Design, and Implementation by Eden Kazman. The goal of this paper is to provide a clear, formal basis for distinguishing between architectural, design, and implementation specifications. Rather than simply categorizing these as levels of detail or abstraction, the paper explores their fundamental differences and how they impact software development. So, why does making these distinctions matter? Clear differentiation between architecture, design, and implementation helps software teams communicate more effectively. It also leads to better documentation, making it easier to track decisions and ensure consistency. Additionally, these distinctions allow teams to make more informed architectural and design choices, leading to more structured and scalable systems. Overall, understanding these distinctions enhances software modeling and improves system design. We selected this paper because it addresses a fundamental challenge in software engineering: how to clearly differentiate between architecture, design, and implementation. The paper provides a framework that helps in making these distinctions more structured and objective. Through this research, we aim to learn the key differences between these three concepts and understand why these distinctions matter in practice. This paper introduces the intention locality thesis, which is a formal framework that helps distinguish between architecture, design, and implementation, and goes further than different levels of abstraction.
Intention versus extension. An intention specification applies to an unbounded number of instances, while an extension specification explicitly lists all possible instances. For example, saying a prime number is a number that divides only by 1 itself is intention, while listing out all prime numbers is extension. Local versus non-local. A local specification applies only to a part of a system, while a non-local specification applies to the whole system. For example, a design rule that affects a single module is local, while an architecture constraint like the layered architecture is non-local because it applies to the entire system.
Architecture is intentional and non-local, meaning it's defined by constraints and affects the entire system. Design is intentional and local, meaning it's defined by constraints and affects specific parts of the system. Implementation is extensional and local, meaning it's defined by explicit details and affects specific parts of the system.
Some challenges include blurred distinction between levels. Intention locality thesis provides clear formal definitions, making it easier to differentiate between the levels. Miscommunication software teams. This technique ensures precise documentation, reducing misunderstanding between the levels. Inconsistent architectural constraint enforcement. Defining which constraints must be non-local and which ones are local helps enforce this rule. How does this compare to other methods? Unlike UML, which lacks strict definitions and causes ambiguity, this thesis is based on formal logic and ontology, ensuring consistency in software structure. It moves beyond informal practices, providing a rigorous framework that helps software engineers to rely on. Why does this technique work? This technique works as it solves a long-lasting confusion between the different levels. This technique also uses mathematical foundation. Looking at the image to the right, which shows the logical formula for a layered structure. These are found due to the software components are being represented by first-order logic. In addition to two specifications mentioned earlier, intention specifications are defined as logical formats with free variables that can be initiated in different ways, while extension specifications define fixed elements without free variables. Now, looking at the logical format to the right, this states that if a component depends on another, it must be in the same or higher layer, ensuring layered architecture is a system-wide constraint, non-local, which is and also is intentional. Ontology is also used, which is a formal categorization of concepts such as architecture versus design. The intention locality thesis provides an ontological foundation to differentiate the software elements based on their scope and level of abstraction. Constraints are also better enforced by clearly distinguishing non-local rules from local rules. By formally defining these constraints using logical rules and ontological classification, the thesis helps maintain architecture integrity, preventing unintended violation, and enables better enforcement through design reviews, automated tools, and structured documentation. Lastly, it finds the law of Demeter is not a designer rule necessarily, but an architecture principle. Law of Demeter is a rule to avoid coupling. It affects all components, making it non-local, and these constraints are not made by specifying elements, making it intentional, which brings to the point that the law of Demeter belongs in an architecture principle. This technique works in large-scale projects as there is a huge need of separation of consume, and these large-scale projects tend to couple with lots of documentation for good communication, in which this technique will assist with precision. In addition, environments like large-scale projects also includes code review and software quality assurance, which can help to check for adherence with the improved architecture.
Do we agree with the author's viewpoint? Yes. The authors effectively establish a framework that defines software architecture, design, and implementation. The use of the intention locality thesis provides a clear and structured way to distinguish between different levels of abstraction in software engineering. The conclusions are logical in theory. The authors demonstrated their intention locality thesis, which showcases the usefulness of the framework. The study lacks strong industry-based empirical data from software engineers. Additionally, the authors did not provide any quantitative data to measure the effectiveness of the proposed framework.